All right, so I'm not sure if I'm the only person who heard that, but just in case, we are recording this meeting, so everybody online, um, just a heads up, we will be recording everything that is being said and spoken to. First off, my name is Colton Marchessault. I'm the president of Vertical Flight Society Arizona. I want to take a quick moment to thank my program directors, Carl Runco, who will be joining with us a little bit later, and Tim Wheeler, who have worked with Dr. Miller to put on this event for us. So thank you to both of them. I'm going to do a couple of quick announcements on our side of things going on in Vertical Flight Society Arizona, and then I actually will pass it over to Daniel Jepp, who is the president of the Philadelphia chapter, and we actually have participants coming over from Philadelphia. So we're happy to have their attendance, and thank you everybody for joining us this evening. Hopefully you can all see my screen. If I can get a quick thumbs up from anybody who's online, just to make sure that you can actually see what I've got up there. Should just be a splash screen. Awesome. Love to see that. Okay. So I'll make it really quick on us today. Our main event that we really want to make sure is being highlighted these days is out here in Arizona. Every other year, we have our own electrical VTOL symposium that goes on. So this is now being called the Transformative Vertical Flight Symposium. So in 2025, Phoenix, Arizona will be hosting the symposium on February 4th, which is a Tuesday all the way through Thursday, February 6th. We do want to highlight that we do like to bring in presenters from industry, particularly on the autonomous side, as that is mostly what we are responsible for. And right now, we are asking that abstracts be submitted to us about September 16th. We are actively looking into possibly delaying this deadline just a little bit longer to give a few more folks time to submit their abstracts. But if you know someone or you yourself are interested in potentially presenting at this conference, please email those abstracts to us at the meetings at az.vtol.org email address. And if you can't remember that, totally okay. Go ahead and head to our website, which is vfsaz.org. You can find the page on there that has all the event information, or you can also go to the headquarters website, which is vtol.org/TVF, which stands for Transformative Vertical Flight 2025. And right now, that's mainly what our chapter is actively pursuing. So I will turn it over to Daniel Jepp of Philadelphia chapter for a couple of quick announcements, and then we'll get Dr. Miller introduced and we'll start our main presentation. So I will stop sharing and pass it over to Dan.
All right, thank you very much, Colton. I don't have anything to share on the screen, so I'll just talk through this. Main announcement from the Philadelphia chapter of the Vertical Flight Society I want to make is that coming up in a couple weeks on September 7th, that's a Saturday, we'll be at Wings and Wheels. It's a local charity event benefiting Angel Flight East, who it's a nonprofit that provides free flights for patients in need of medical treatment that are, need to go somewhere far away from their home. The event runs from 11 a.m. to 4 p.m. and it's in Philadelphia area town called Bluebell, Pennsylvania. If there's any information people want from this, we have something up on our website, which is ifsphilly.org. Hopefully easy to remember. Other than that, we hope people are able to make it out if they'd like to. And otherwise, keep in touch on our emails to see if, future events from us. All that said, back to you, Colton.
Awesome. Thanks, Dan. Thank you again for attending today, too. We're happy to have you. We'll go ahead and introduce our guest speaker today, and then we'll start with the presentation. So, Dr. Mark A. Miller. Um, His research at Penn State focuses on the fundamental fluid dynamics of unsteady and rotating systems by using a multifaceted experimental and theoretical approach. Now, I do want to take a minute to talk a little bit. Well, I guess overall this, I want to make sure I give the full length of detail here because Dr. Miller is very involved in the field of vertical lift. So bear with me for a second. But his ongoing projects span a wide range of fluid systems, including multi-rotor electric vertical takeoff and landing, or eVTOL, performance and acoustic characterization, wind turbine aerodynamics and acoustics, turbulent structure modifications due to roughness, and development of innovative sensor systems which are tailored to these specific flow regimes. He's an active member of the American Physical Society, the AIAA, where he serves on the Fluid Dynamics Technical Committee, and the Vertical Flight Society, where he serves on the Test and Evaluation Committee. So, with that, I will turn it over to Dr. Miller.
All right. Thank you, Colton, and thank you all for joining today, especially if you're on the East Coast like me. I know it's a little bit later. I did try and put plenty of pictures in this presentation, so hopefully that keeps you interested. So yeah, today I'm going to be talking a little bit about some of the work we're doing here at Penn State. And the whole idea of this work is we we at the university scale would like to be able to study full-scale aerodynamics, especially. But that brings with it some challenges that I'll talk about. So we're kind of approaching this from a different perspective and looking at using a compressed air environment to test these small-scale rotors. So before I get into that, though, I really did want to take a second to thank all the research team. It's really the students who are doing all the work for this, designing experiments, installing things, crawling around the wind tunnel and stuff like that. So here are the students here on the bottom, and then my collaborators here at the top here at Penn State. Okay, so what's the question that we want to look at? And I was really excited to receive this invitation to talk. I know the Arizona chapter does have a focus on eVTOL work, and that's actually been our focus too. So the question that we're interested in answering, though, is how does kind of the size or scale of these aircraft affect their performance? It is going to be significantly different than kind of a drone scale at the extreme side of that. And I'll talk a little bit about the acoustics, perhaps if we have some time, some ongoing work that we're doing, but mainly we'll focus on the aerodynamic performance. And if you only have one 6-foot rotor, these are a lot smaller than kind of the typical single main rotor helicopter that we've been studying for decades. And if you just think of it as being a 10 times smaller rotor, it might not seem that complicated. The issue is that you not only have one, but many rotors, and they're all interacting, and that can lead to a lot of aerodynamic complexity. Things like, interactional aerodynamics, where you have kind of one wake being ingested by another rotor. You can also have a lot of unsteadiness in the flow from dynamic stall of multiple rotors, and those wakes can be interacting as well. You can also have things occurring like transition on the blades, and that can change depending on the size that you build your rotorcraft system at. And all of these, like I said, are going to be in some way or another affected by Reynolds number. And we've decided to really focus in on eVTOLs because it is a little bit of an unexplored design space. There are a lot of different configurations out there. They're all really interesting, I think. I'm a fluids aerodynamics person, so all this complexity has us kind of excited, but there's also a lot of unknowns. So our goal here is to really explore the design space, maybe provide some insight into how the aerodynamics change as you go, especially from model, which is easy for us to kind of build and look at in the lab, to full flight scale, right? So that's kind of the question that we want to answer today. Okay, so that's kind of our motivation. This is just a really brief overview of what I'll be talking about. Talking a little bit about the scaling background and why we're doing what we're doing, and also introducing our new facility. So we'll jump right into that. There are many things that we want to match when we go to do an experiment. And experiments are very expensive, so we want to match as many as we can, depending on what our objectives are. The three main ones for single main rotor helicopter testing and eVTOLs as well are going to be Reynolds number. So that's people typically will call the scale or size effect. Mach number, so these will drive, if you have a high forward flight speed, and also will drive the acoustics that the aircraft generates. And then we're also going to be, if you're doing especially large single main rotors, things like the blade elasticity, lock number, so the inertia of the blade. Today, we're gonna go ahead and simplify because we have a limited amount of time, and we're gonna focus mainly on rigid rotors for eVTOLs today. And if you look back through the literature, this is not exactly an unknown challenge. And the Singleton paper from over 20 years ago points this out quite well. It is not possible to match full scale tip Mach numbers and Reynolds numbers if you make a model and you test it in air. It's just not physically possible. And even earlier, Keys mentions that if you do have a Reynolds number issue, this is going to be the primary cause of difference between hover performance and model test data. And today I'm going to be talking a lot about hover and some limited axial climb cases. So these are very relevant to us and well known in single main helicopter rotor. Okay, so if you're looking at this from a non-dimensional perspective, we're going to have, like I said, today just the two two main parameters, Reynolds number and Mach number. Here written kind of in terms of the rotor important parameters. So omega is our rotation rate, R the radius, C the chord. And then we have our fluid properties, rho and mu, and the sonic speed, A. The problem is, and this is exactly what was pointed out by those previous authors, is that you can't match these simultaneously because they're coupled through omega R, which is kind of like it's just the velocity at the blade tip, right? And if you rewrite Reynolds number, it's just going to be a function of Mach number, your chord, which is going to be a function of the size of your helicopter, and then also your fluid properties. So we're kind of stuck. And that Reynolds number is always, if you imagine if you shrink a rotor down 10 times, the chord's going to have to shrink 10 times. So you still have this 10 times smaller chord, which causes a problem for Reynolds number, unless we can do something else, right? So if we could somehow change the fluid properties, maybe increase the density while keeping viscosity the same, which is what we can do actually in compressed air, we can now tune Reynolds number completely separately from the Mach number. And that's kind of a nice tool to have in your pocket. So just to kind of ground this, if let's say we just have a little, 18 centimeter kind of toy size model, and we take that now carefully designed model and put it in a high pressure environment. So we increase the density, we increase the pressure. Those are, you can think of this kind of like effectively increasing the diameter. So if we took that little model, 18 centimeters, and we put it in 6 atmospheres of pressure, we had a tank full of air, we stuck this rotor in there, that would actually be the same aerodynamically as testing almost a 1.5 meter diameter. And this continues to go up. So if we go up to 34 atmospheres, that would be about a little over a 6 meter diameter rotor. So for a very low cost, small scale facility and some pressure, need a few compressors, we could get much larger equivalent full sizes. So whenever you see pressure or density, you can really think, and those values are increasing, you can really think about that as I'm effectively making the rotor bigger aerodynamically, right? Even though we're physically using the same size model. So hopefully that makes sense. And again, this is not exactly a brand new idea either. I'll talk a little bit about that as well. But to our knowledge, we're the first people to try this with compressed air. So this allows us to achieve proper scaling on the rotor, and we'd like to generate some of these comparison data sets. Now, in the future, unfortunately, we don't have a lot of results yet looking at these kind of interesting eVTOL configurations, but that's coming. So we're actually working right now over the summer at testing multi-rotor and some coaxial cases. And this ability to do these unconventional kind of strange or unusual configurations is really nice in the lab because it's a lot lower cost and a lot cheaper. So this is a facility that we're going to be using to do that. And I'll talk about that on the next few slides. It's basically a very large pressure vessel that we've built a wind tunnel inside of. And it's actually circular. So it's kind of a weird pressure vessel. It loops back on itself, as you can kind of see here in these little schematics here at the bottom. It has a lot of things inside of it, like flow conditioning and a fan that turn it into a wind tunnel. And the way we run this, it's not a high-speed facility. We actually just fill it with compressed air, and then we circulate the air around in a loop. So it's a single return wind tunnel. You can kind of see from the students here working on the tunnel, it is, for a university, fairly large-scale facility. That's nice because we can put fairly large models into it. Now, all that being said, with our about 1 meter diameter test section and the velocities that we can get, about 45 feet per second-ish, and I'm switching back and forth between units, we can get about 34 million Reynolds number per meter or 10 million per foot. So, okay, great. Those have million in them. They sound like big numbers. So I thought I would throw one simple example. Let's say you just had a little, 25 millimeter 1-inch airfoil, and you put that inside the tunnel. That would have a Reynolds number of 850,000, which is 34 times what it would have in atmospheric pressure. So very high. I also thought it'd be interesting if I threw in an example more related to rotorcraft. So let's not worry about rotation yet. Let's just say I take a example, large-scale rotorcraft, and I want to shrink that example down so that I can study it a little bit more easily in the lab. So I want to take something that's on the order of 15, 16 meters long and make it about a meter long. So it's still a pretty big model, but very reasonable to do in this size facility. Now, if you were going to look at if you wanted to know, let's say, the drag on this fuselage in cruise, you could, at the full scale, you would need a Reynolds number of, to match this is your matching condition, of about 82 million. Now, if you made this 1 meter model and tested it just in atmospheric air, you would only get a Reynolds number of a little under 1 million, kind of at this particular case. However, if you compress the air, we have this 34 times multiplier, right? 34 atmospheres of pressure, then we would get the same order of magnitude Reynolds number as full scale. So, and that's without using high speed. We're just using pressure to get that, really. So this kind of hopefully highlights the utility of using pressure. The other cool thing is we can get any scale in between there. So we can go up to something that's really close to full scale. We can go to small scale, and with the same model, by changing the pressure only, we can basically simulate any size in between. So I kind of call it a spectrum of scales, if you want to think about it that way, going from the small to the large. So hopefully that makes sense. Here's just a peek. I know I put a lot of pictures in here, like I mentioned. This is just inside the tunnel. We have a fan. It does spin. We have a test section, like I said, about 1 meter, just with some instrumentation shown. Kind of a look through the contraction. And this is all inside the pressure vessel, right? So we've built all this hardware to make sure that the flow is uniform, low turbulence, like a usual wind tunnel should be. Okay, so let's take a look at some data. We're going to mainly be focusing on experiments that were performed in the test section. We have done some other things. I'm happy to talk afterwards if you're curious about some of the other work we've been doing. If you're also curious about how we get inside, we actually have a little hatch over here, and you have to kind of shimmy your way inside, but you can easily fit, and actually, you can easily stand up in this section, which is about 8 feet here. So it's quite a large facility. So this is the rotor we're going to be looking at. The whole goal of this work, and like I said, this data was taken this year, so this is still very new. And this concept, we wanted to verify it first. So we took this relatively simple rotor geometry, and I'll explain why we picked this in a second. It's just a 2-bladed, fixed pitch, machined, high tolerance machine aluminum rotor. What I want to point out is it's exactly scaled. So the chord to radius ratio is the same. The airfoils are the same as full scale. This is a picture of it in the tunnel with our test stand. And, we can measure tunnel velocity, and it's about 32 centimeters in diameter, roughly. This is just a look at our load, measurement apparatus. We have a motor that spins the rotor. We have a load cell that measures the reaction torque, and that allows you to get the power and the thrust that is generated or required by the rotor. So why do we pick this rotor? There was a good reason. This is actually a NASA project that funded the original development of this rotor, called Dragonfly. And the goal of this project was to build this pretty unique large drone to fly on Titan, which is one of the moons of Saturn. And it's a very high density atmosphere there. So it's actually a perfect case for a vertical lift vehicle to very easily generate a lot of lift without a whole lot of rotor. And they did a lot of these tests of this rotor geometry at the NASA TDT facility, and it's all available. So there's not a lot of data for coaxial rotors that's publicly available with a known rotor geometry. So that was why we picked this. They also did a lot of tests with just the single rotor. So it kind of is the perfect comparison case there. So they only really tested, one of these multiple coaxial configurations. So let's quickly look through the full-scale data set that what's available already. So like I said, they tested all of these different configurations at the NASA Transonic Dynamics tunnel. And they also tested, which was really cool for us, in 2 different gases. So like I said, we're not the first to think of this heavy gas changing the fluid properties. I mean, NASA's known about this forever, since the 30s at least. But they have refrigerant, which has its own benefits, but it's heavier than air. And depending on the refrigerant you use, you get a different boost in Reynolds number. Today, we're just going to be focusing on really the single rotor case. And then they tested both in air and in heavy gas. So we'll be looking at their data for this one rotor in both of those and comparing it to our case. So let's dive into that. Before we look at any actual results, I wanted to orient you with respect to the operating space. So down here on the x-axis, we have Reynolds number, and this is just kind of an idea of the scale that's most relevant to the rotor. So it's calculated at about 75% out from the hub. And that's just kind of dynamically relevant to the blade boundary layer. We can have a whole discussion about Reynolds numbers and why you should choose them, but that's for another time. So we assume that to be the most dynamically relevant. And one of the interesting side notes, it actually doesn't matter what Reynolds number you pick when you exactly scale the geometry like we have. But anyways, I won't get on a tangent on that. I'll just mention that up here on the leftmost axis, we have Mach numbers. So each one of these points represents an operating point that they tested in the TDT. And then we've also added in these kind of triangles here where we could operate just at atmospheric air. So if you have a 32 centimeter model, you would see you'd be very limited in your Reynolds number range. We wouldn't be able to even get close. No matter, you could keep spinning this rotor faster and faster, and you still would be very limited, and then you'd be getting into some Mach number effects. Now, if we also add on the NASA data, so this is the 135 centimeter rotor they tested both in air, so this is kind of the in-between points here, and also the heavy gas. And you can see that increasing the density of the fluid really does give you a big boost in Reynolds number. So that's the only difference. Actually, the same rotor, just in these two different configurations. And as you can tell, to move from the left to the right on this operating space, you really need to either build a bigger rotor or have a higher density working fluid. So what we can do is, now that we have this pressurized facility, one more note, sorry, is if you're wondering why these all kind of fall in the same vertical line, it's because all they're doing is increasing the RPM. So each one of these vertical lines is just an RPM sweep, but we've non-dimensionalized everything. Okay, so if we're now going to look at the Penn State facility, what you can see is, and each one of these lines is actually increase of 1 atmosphere in pressure. So we're just literally, opening a valve, filling another atmosphere, another about 15 PSI of air into the tank. And you can see now, by doing that with this same model, we're able to actually span a huge range of Reynolds numbers and Mach numbers. This is, like I said, only the background pressure is being changed. And you can see we need about, a little over 4 atmospheres to get the 135 centimeter rotor, and a little, about 11.5 atmospheres to do the heavy gas, which is very easy for us. This is actually like the low end of our capabilities. As an example of that, if we were to pressurize to the max, which is 34 atmospheres, this would be the same as testing an 11-meter diameter rotor, which really you couldn't do except maybe in the world's biggest wind tunnel, the NASA Ames NFAC facility. Like TDT would be not big enough for a 36-foot rotor. So hopefully this kind of highlights where we're able to operate and why. And I'll quickly dive into some hover testing. I'm going to throw this data up really quick, and then we'll talk about it. It's a little bit different. So now we're looking still at Reynolds number, Mach number on X and Y axis. But what I've done is plotted points, and each one of those points has a color code that corresponds to the thrust value. So this is non-dimensional thrust, which is how we have to compare everything non-dimensionally. And you can see here, each one of these lines is, again, a different pressure. So, from 1 to 10, 11-ish atmospheres. And what's interesting is there's actually not a lot of change here. So if you were hoping to see big scale effects to validate the use of this facility, they're not evident, at least in thrust. We also don't really see much change in Mach number as you go, from the bottom to the top of this plot. There's not a whole lot of difference here. And I'll talk about that in a second and why that's actually what you would expect based on some basic theory. Now, it's a little different if we look at power coefficients. So this is basically, how efficiently is your rotor able to produce power? And what's interesting is, or how much power your rotor takes, right? What's interesting is that the story is a little different here, is at low Reynolds number. So on the left of this plot, and I'm not sure if you can see my cursor or not. I won't get too crazy with that, but on the left side of this plot, you can see at low Reynolds number, we actually have much higher power that is required. So we're up here kind of closer to 9, 10 to the minus 4. However, as you increase Reynolds number, you actually drop off in your required power. And this has been as actually a pretty well-known effect that at small scale, you need much more power than you do at large scale or at full scale. Now, what's also interesting is this levels off at high enough Reynolds numbers. So you get above about 300,000-ish range for this particular rotor, and there's really not any change. You know, I can throw some numbers up here about how little that change actually is that we've measured, but, you know, it is very small. And we also, again, don't really see a huge Mach number dependence. So going from top to bottom here, there's very little change depending on Mach number, which you would expect, right? We're at very low tip Mach numbers, maybe than what some of you are even used to. So we're very much in the incompressible regime right now. Okay, so I'm going to briefly go through the momentum theory. If this isn't your thing, feel free to tune out. But really, it's just cracking open your favorite rotorcraft textbook. Here I have a copy of Leishman, always sitting on my desk. And let's say, you know, we're just trying to explain these trends we saw. You know, not much change in thrust and a little bit change in the power, or a little change in power. And let's just try and estimate what we would be operating at for this rotor. So for an eVTOL style rotor, pretty high solidity. I threw some numbers in here. We get a, you know, straight bladed pitch. We're not even twisting the blades, which is what these let's not get too much into the details. We're just going to estimate, right? Back of the envelope. A pitch of about 9 degrees. Okay. If we dive a little bit deeper and we say, well, how is thrust and power generated on the rotor? You know, you need a little bit of blade element to get some insight into that. But basically, each little piece of the blade contributes its own amount of thrust and power. And you can break that down into the individual lift and drag components, which is just 1D momentum theory, and the blade element part of that. And you can see you get this kind of dependence. We have lift and drag coefficient, and then that depends on phi, which is kind of like the flow angle, which is made up of alpha, the angle of attack, and the relative pitch angle. So we calculated that. Now, what's nice is that in hover, we can really simplify things. We can basically say, you know, phi is very small because the only velocity we have is any induced velocity, because the rotor creates a small pressure difference. And that means that we can simplify our thrust, and now I've written it as a coefficient. And that just helps simplify things a little bit. You can see we have some geometry dependent terms. We have delta R, which is just the slice width, and then we have the radial location R, and then sigma is just our solidity at that location, and then lift. So really, what this is saying is our thrust coefficient, in hover at least, should only depend on lift, and any changes in lift that are dependent on Reynolds number. Power is a little different. So because CL is generally at least an order of magnitude bigger than drag, usually more, but you have a small value of phi because inflow angle is small in hover, those two terms actually kind of fight each other. So this phi, CL, and CD are actually in competition. So we would expect that if there are changes in CD, the drag coefficient, it's going to really show up in power and not in thrust. And that's actually exactly what we saw. So if you look at some airfoil data, what you'll see is generally if you're at a not stalled condition, which hover isn't, you're going to, at least at these, you know, idealized pitch cases, you're not going to see much change in lift, but you may see some change in drag. So again, this is why we would expect to see changes in power, but not thrust maybe. You know, lift generally, there might be some small changes you could pick up, but the big changes that you're going to see are going to be in drag. And that, so yeah, lift remains more or less fixed at our given angle. And again, angle of attack here is about the same as theta, just because we're in hover. And that's exactly what we saw, right? So this is just those two plots from before. Very little change in thrust, a definite dependence in lift. And if you look back at this airfoil data, you'll see as Reynolds number increases, you actually get less drag. And that's due to some complicated transition happening on the airfoils. But what's cool is you can kind of see that effect in aggregate on the whole rotor. And we can pick that up very easily with this data set. Okay, so let's talk about axial climb. And I won't have as much theory in here, I promise. We did do a limited range of axial climb cases. And the reason we did this first was basically with the stand we have, it was the easiest configuration for us to test in. Like I said, ongoing work is expanding this. But for now, we're also only going to be comparing to NASA cases that are in a similar range of mu and Mach number. We also identified earlier that Mach number effects are not really that significant, so we're actually just going to we're not going to ignore them. We've done the analysis. They don't really play a role here. So for clarity, I'm just not going to denote the individual Mach numbers, but those are still changing. They're just not playing a critical role in the performance at these cases. Okay, so I know this is another plot. Things are a little different with this one though. So on the x-axis, it's still Reynolds number. On the vertical axis, I've instead plotted the thrust coefficient. So I've kind of swapped the color map. Because now we have a third variable, which is advance ratio, right? So instead here, advance ratio is coded. If you don't like color coding, that's fine. I also just threw up kind of the approximate mu values. And what you can see here is basically as you increase Reynolds number, you can see for hover, so hover we already looked at just in a different way, but you can really see that it pretty much flatlines after you get Reynolds number high enough. Mu generally the same is true, although these higher advance ratios have a little bit more variation in the data points. And that is primarily due to two reasons. There is a lot more unsteadiness at low Reynolds number. So like we said before, transition on the airfoils, dynamic stall might be changing if it's happening. In this case, it probably isn't, but any of those weird transition effects, the boundary layer is also very sensitive to any other things going on in the flow, like turbulence or roughness. So any of those little, or some temperature change or whatever, right, can cause transition at low Reynolds numbers, which is kind of why it makes it very tricky to measure there. And also your loads are quite small. So we kind of expect more uncertainty at these left side of this plot. However, as you increase Reynolds number, everything converges. And that's really what you would expect to see. Your loads get higher, but also your transition point on the airfoil becomes relatively stable near the leading edge. So you have mostly turbulent boundary layer, and that kind of just fixes everything as you keep increasing Reynolds number. Now, what happens as you go to high advance ratios is, you're basically unloading the rotor because some of that incoming flow is doing some of that work for you. And then you're back to this problem of measuring very small values, very small thrust loads. So that's probably why we see more scatter. Now, if you look at the NASA data, which is here shown in these triangles, you can see there's even more scatter and less data points. So to their credit, this was not the case they were most interested in. It's just the case we chose to compare to. However, it does kind of highlight that we can get very high density data points in these very challenging regimes of this kind of low, moderate Reynolds number, as well as going much higher. We're only showing the lower cases because that's where all of our trends were. Okay, so moving on, we can sort of play the same trick we did before and just say, let's look at the high Reynolds number limit though. So let's say the data is not varying much above about 300,000. And let's just average those data points above this limit. And what that does is allow you to get basically the full scale thrust, and we'll do power in a second, but the full scale thrust values for this rotor. And instead taken on this, very small model. And that's kind of a very useful thing that you can do. You may not need to go to the full tunnel pressure to get to those cases. You may actually be able to observe this Reynolds invariance. And what's happening in the flow is the Reynolds number is high enough where you fix transition and your inertia effects are kind of dominating. And so that's kind of another neat feature of this flow. So let's look at power also. Now, if you look, I've also plotted hover here. And so we've already looked at that data. It's just in a different format, kind of looking at it edge on instead of from the top down, because we have CP here on the y-axis. Here, mu again is advance ratio. And you can kind of see a similar thing where at high Reynolds number, our power generally decreases, especially evident in the hover case here. Now, our uncertainty also decreases, kind of indicated by these just standard deviation bars that I have put in here on orange. You also notice the standard deviation of the NASA data sets is going to be a little bit higher. Again, it's just a difficult regime to measure. Their setup wasn't really designed to do this. But I think it just shows that there there's a operating space where doing compressed air testing can be very enlightening, before or in concert with doing other tests. Now, what's interesting is we do see this decreasing trend in required power as you increase Reynolds number, and it really does hold for all advanced ratios that we tested. So this is, for this particular rotor, probably a fairly universal phenomena, at least in hover and axial climb, that you generally will need less power as you increase Reynolds number. And we can do the same thing. We can say, let's establish a cutoff Reynolds number, and above that, we're going to call that the high Reynolds number limit. Now, you could argue over where that should be. Maybe it should be 400,000, 300,000, 500,000. The nice thing is you have enough data points here. You could pretty objectively, you could not be super subjective about this. You could just identify what your cutoff is and then what this sort of spread that you see if you assume that cutoff Reynolds number value. So we did that here for power. I'm just going to put some numbers up. You can see, below an advanced ratio of 0.049, you basically see kind of a fixed required power, whereas you see slight decreases as you keep going higher and higher in advanced ratio. So here's a big table of results. I'm not going to go through all of this. The whole point of this is that we agree very well with the TDT data, easily within the uncertainty of our measurements, but certainly within the uncertainty of their measurements. And we have a lot more data points to pull from. So if you look at this top, I've just, put a number next to this high Reynolds number hover data average is an average. So we're averaging, above this 300,000. So this dashed line that we showed earlier. This data point has been averaged over 41 individual tests over a wide range of Reynolds numbers, whereas this data point was only from 2. And again, we're not trying to say the TDT data is bad. They were really interested in some axial climb cases and other cases, especially the very high Reynolds number. We were really interested in scaling, which all happens at the difficult end of the spectrum, right? From that kind of few 100,000 to maybe a couple million Reynolds number. And within that range, we agree very well with their data. Our data is slightly higher on average, but again, that may be due to some of the uncertainty in the measurements. Okay, so some conclusions real quick. The compressed air testing has been verified for the single rotor case against this really neat air and heavy gas data set, which also used the same concept, just at a larger scale. And we clearly saw the scaling trends, so the Reynolds number dependence in TDT result, and that were not available from the TDT results. We were able to pick those out. What was also a little bit funny about this test is the Dragonfly rotor. If you read the Marshall paper that this data is from, which I think I cited earlier. If not, I can throw that up later. They designed that rotor to not be sensitive to Reynolds number. So we picked a very difficult case to compare against, and it appears that rotor achieved its stated design goals. There wasn't any measurable change that we could detect when Reynolds number was above about 300,000, and only small increases were required if you go below 300,000. About 15% additional power is generally required above or below a Reynolds number of 300,000, and your thrust you can expect to basically be the same. So this actually is a pretty good candidate rotor for small scale testing if you would like to do that sort of thing. We also found that for axial climb, these results generally hold. The trends are basically the exact same within our experimental uncertainty. Okay, so we did measure slightly larger thrust and power in all fairness. We do have much higher data point density and lower uncertainty levels just because of how the experiment was designed. Like I mentioned, we are continuing to explore this testing method for descent and forward flight. So keep an eye out for that data. We're hoping to maybe present it either at next VFS or next AIAA Aviation. Well, it just kind of depends on timing. So keep an eye out for that. And I wanted to also quickly show mostly pictures of some other ongoing work that we have at Penn State before I take some questions, just because I think it's cool, and hopefully you will too. We have this interesting problem in the wind energy field, so also rotor-related, rotor-driven field, where rotors are getting absolutely enormous. You know, it's projected that in a little more than 10 years, we're going to have rotors that are almost 500 feet in diameter. Those are absolutely enormous. And the question is, for really any of these rotor sizes, how do you scale this down and study it? It's kind of the same problem we have for rotorcraft. How do you effectively scale something down? Because it also has a rotational dependence. And even with compressed air or the world's largest wind tunnel, we actually wouldn't be able to achieve these conditions. So this ongoing project is trying to figure out a physics-based way of scaling the wake. And this was really performed by a colleague of mine, Dr. Sven Schmitz, and his PhD student, Desiree Major, who has since graduated. And the cool thing is, if we could scale the wake properly, this is now looking behind the rotor, not just at power and thrust, but what happens downstream of that. And this is important if you're laying out a wind farm, right? It could be important also for rotorcraft if, you know, we have these multi-rotor interactions. And they have done a lot of really neat computational fluid dynamics and published a paper, which I'd be happy to send you, on how you scale these wakes so that they're exactly the same in the mean velocity. So this is kind of a neat way of looking at the rotor from kind of an induced power perspective. And we're going to actually be doing some experiments in our wind tunnel to verify their simulations. So they've designed this rotor. It looks kind of funky, but it actually has the same wake velocity profile as the full scale several 100-meter turbine. So the full scale has this enormous Reynolds number, and we're still pretty high for a wind tunnel experiment, but we can't get to 124 million. But interestingly, if you plot the velocity profile behind this rotor, it looks basically exactly the same. And these are all different cases. The experimental data is not there. The Penn State data is actually the CFD data. So these CFD results have compared to full scale to model scale. And then they've also predicted this for some other facilities. So some ongoing work is that we're actually measuring, these pictures are actually from this week. So it's been an ongoing project to spin this rotor in our tunnel and then measure some wake profiles behind it. And that we think this could have some interesting impacts and applications for rotorcraft people who would want to create a scaled wake behind a rotor. And actually was inspired by some work that's been done in the rotorcraft field. So happy to talk more about that if you'd like. With that, I will thank you for your attention and staying with us through this, and also like to acknowledge the funding from Vertical Lift Center of Excellence with our director, Ed Smith. And yeah, here's how to get in contact with us if you'd like to chat some more, and I'm happy to take any of your questions. So thank you.
Awesome job, Mark. Thank you very much. So we will turn it over to everybody in the audience. There is at least one question that's in the chat window, but I thought I would quickly open it to those that have microphones. If you would like to ask a question, please use the reactions bar at the bottom of your screen to raise your hand, and we'll call on you to unmute your microphone. Otherwise, I'll go to our chat question from Shreyas.
Let's see. I guess while we're waiting, I can check out the chat. So I have a couple monitors, so I'm not always looking right at the camera.
Totally okay.
Shreyas was asking about the material of the load cell. Yes, so this is something we've noticed in a lot of our other testing, that if you have a very large energy source, they're strain gauge based instruments, these load cells, so you do have to thermally isolate them. We generally use Garolite or FR4. It's kind of like it's just a fiberglass kind of machinable composite material. It works really well. Happy to send you some details. We have not had any problems since we started doing this. Before, we would. You do have to also keep an eye on your flow temperature, but as long as it's uniform on the top and bottom of the load cell, you're generally fine. So we usually mount thermistors. I didn't show that, but we mount thermistors to make sure we're at the same temperature on the top and bottom. It's the gradient in temperature that really gets you. So hopefully that helps. And then there was another question. Measuring prop loads is challenging. Yes. Vibrational noise. Yes, we definitely have these challenges also. First natural frequency of the tunnel. Are there any designs in the compressed tunnel to minimize this effect or measures taken into account for such possible effects? Yes, also a very good question. What's nice about model testing is that you can spin you have to spin much faster than the full scale in order to get to that condition. Now, our wind tunnel is fairly low speed. We can't do like really high forward flight speeds, although we can do forward flight Reynolds numbers. So what that means is our tunnel velocities and our tunnel frequencies from the fan are much lower, like by a factor of 5 to 10 lower than our rotor, which is which is about 5 times smaller than our tunnel fan. So yes, it is a problem. We do balance the rotors, and that's something that we're working on improving actually. But yes, you do have to be very careful about rotor balance, any imbalance, also any stand vibration. And you probably saw our stand was kind of hefty with lots of guy wires. We actually have a new version of that that's a little bit more streamlined, but you do have to have either a very rigid stand or specially designed stand with a lower natural frequency. So yes, definitely something to watch out for when you're testing. Hopefully I answered that question.
And in case it didn't, feel free to take a, it sounds like you did. I was going to say, feel free to take a minute if you'd like to respond to that at all. We do obviously have a couple more minutes on the time block, so we can use that if we have any more questions from the audience. Again, feel free to use the reactions button, raise your hand if you'd like us to call on you and open up your microphone. We'll give it a few minutes to go around the room. Otherwise, we can also close out for the afternoon too. So we give a minute or two. Also, I suppose we could enter into the chat room. Also making sure that my microphone is not too loud. I have my dogs fighting in the background. I probably apologize for that. Okay. Well, I certainly won't have us sit here too much longer on that. So, Dr. Miller, I really appreciate your time today. I'm going to make sure that did not just refresh on a new one. Yep. Thank you, Ariel. Thank you for those of you who joined us today. Appreciate your time in here as well. Again, if you need to get a hold of Dr. Miller, all of his information is here. So please feel free to reach out. If you need to get a hold of any of us on the Vertical Flight Society side of things, again, please visit our website, vfsaz.org, and you'll find all of our contact information there if you'd like to reach out to us. Otherwise, I think we can conclude this presentation for today. So again, Dr. Miller, thank you very much. We appreciate your time.
Yes, thank you, Colton, for organizing. And yeah, thank you everyone for joining. I do really appreciate your time, and please feel free to reach out. We love talking to people about interesting aerodynamics problems. And if anybody wants to measure fuselage drag, that's something we've been trying to explore. So feel free to send us an email. But yes, thank you all.
It's an interesting thought, actually. All right. Yeah. And actually, as Ariel's putting in here too, if you have interest, as I mentioned too, that conference that we hold out here in February, we would be certainly interested. If you have an abstract you're interested in submitting and potentially presenting, please get a hold of us. You can work through Carl and myself or any of the names that you know.
Okay, great. Yeah, we'll definitely chat about that. That's a very interesting conference. So thank you.
It is very specific in the field too. It doesn't span everything vertical lift. So. All right, everybody. Well, thank you again for joining today. We'll let you go for the rest of your afternoon. Have a good, I guess, rest of your evening, and we'll talk to you next time.